Welcome back to Inorganic TUTOR'S Institute. In today's lecture, we are going to solve about 20 multiple advanced calculus 2 problems, all right? And we are going to dive into various kinds of questions that will enhance our understanding in calculus 2, right? In our previous lecture where we as well solved about 20 questions, we explore on different kinds of questions. In here, we are going to explore on another different kind of questions again. Right. So let's dive into it. Our first question is, we want to find the vector equation of the line, given that the Cartesian equation of the line is this, right? So if you have a question of this nature, first, simplify the expression. Okay, so this is the I component, this is the J component, and this is the K component, right? So represent in here, step one, simplify the expression. Okay, simplify the expression. So in doing that, first step, right, make sure you let each of the components have a common ratio, right? So let's say that we are using t. So let's say we're saying that t should be equal to what? The first component, which is 3x plus 2 all over -1. And the second component 2 equals what? T equals 2y minus 1 all over 4. And the third component also t equals 5z all over what? 3. Right? So if this is the case, you see they all have the same ratio, common ratio, t, right? So in here, we want to find the vector equation of the line, right? So we have to make sure that we make s the subject in here, make y the subject in here, and make z the subject in here, right? So we are going to make s the subject in this expression. So we're going to say that minus t equals 3x plus 2, right? So we're going to simplify this and make t the x the subject, right? So we're going to have 3x equals minus t minus 2, right? So we have x equals minus t minus 2 all over 3, right? So we can say that our x is equal to minus 1 over 3 into t plus 2, right? So this is our x component, right? So the same thing applies to this part. So we're going to say that y equals 2y minus 1 all over 4, right? So making this is t, right? So making y the subject, we're going to have 4t equals 2y minus 1, right? So we need y. So we say that 4t plus 1 should be equal to what? 2y. So we say that 2y is equal to 4t plus 1. Divide here by 2, here by 2. So we have y equals 4t over 2 plus half, right? So we have y equals 2t plus half, right? So this is the y component, okay? The same thing applies to the last component. So we are going to make z the subject as well. So in here, we say that t should be equal to what? 5z over 3, right? So making z the subject, we're going to have 3t equals 5z, right? So z will be what? 3t over what? 5, right? So we have the x as this, we have the y, and we have the z, right? So in as much as we have all this, then we can say that our equation the vector equation of the line will be r of t equals -1 on 3 into t plus 2. That is the I component. Then the second part is going to be plus half plus 2t or j plus 3t over 5k, right? So that is our vector equation of the line, right? So this, we can as well use the angle brackets to represent our final solution. So we can see that we have -1 on 3 using the angle bracket, -1 on 3 into t plus 2, comma 1 on 2 plus 2t, comma 3t on 5. Right, so this becomes our vector equation of the line. So if you have any question of this form, first of all, represent each component by a ratio, and the ratio should be common to all. So if you are using t equals this, the same t should be equal to this, the same t should be equal to this, so that when you make x the subject, you make y the subject, you make z the subject, you're going to have all the, you have x in terms of what? T. You have y in terms of t, and you have what? Z in terms of t. So that is the process we go through to find the equation, vector equation of a line, given the Cartesian equation. All right, so let's move on to question. Okay, so with question number 2, we are given the vector equation of a circle as r of t equals a cos ti plus a sin tj for 0 less than or equal to t less than or equal to what? 2 pi. Okay, and we want to use the arc length formula to find the circumference of this particular, to find the circumference. All right, so first of all, we know that arc length, if you want to find the arc length, is this from lower limit a to upper limit what? B. Then we find the magnitude of the differential radius. So magnitude of what? Differential radius, right? The r dt, the r dt, right? Or we say that L is equal to a to b r prime of t dt, right? So this and this, they are all the same, right? So looking at this, what we need is to find the derivative of the radius, right? Then take the magnitude of it. Once we have that, the rest is what? Computations. You know that in here, our a is what? 0. And our b is what? 2 pi. That is the range that we have been given. Okay, so once we know this information, then the rest is what? Computation. So we know that r of t is equal to a cos t I plus b sine t d, right? So r prime of t will be equal to, we differentiate the first term, which is a. A is a constant, so when you differentiate, you have 0. So there is no need to touch that. So we have that maintained. Then we differentiate the second term, we have what? Negative sign. So we're going to have negative sign, right? Differential, of course, is negative sign. So we have negative sign ti, then plus b cos tj, right? Differential of sine is cos, right? So this is the differential of what? The radius. Now we need magnitude of this. So that is going to be r prime of t, magnitude of that equals square root of negative a sine t all squared plus b cos t d all squared, right? So we're going to have a squared sine squared t plus b squared cos squared t, right? So I guess all of them are a, right? The notations all are a. So in here is a, here too is a, right? So we're going to have magnitude of the differential radius to be, you know that a is common to all the terms. So we're going to factor a in the square root sign. Then we have sine squared t plus cos squared t, right? And you know that this is an identity of which is going to give us 1. So we're going to have square root of a squared into 1. And that is square root of a squared. And that is basically a. So we have this to be what? A. Okay, so we have the magnitude of the differential radius to what? A. So we're going to substitute into the formula that we have from 0 to 2 pi of a dt. This is a constant, right? So we can factor that out. So we factor that out. Then we have 1 dt. When you integrate 1 dt, you're going to have t plus a constant. But you know, this is a definite integration, so there's no constant. So we're going to have a out, t from 0 to 2 pi here. So we're going to substitute the limit inside. So when you substitute 2 pi, you're going to have 2 pi. So we're going to have, this implies that we're going to have a into 2 pi minus 0, right? So we're going to have a into 2 pi. Okay, so this is the result. So we can say that our length, our arc length is a into 2 pi, of which is equal to 2 a pi, or 2 pi a. 2 pi a. Okay, so this is the process we go through to find the arc length, using the arc length formula to find the circumference, given the vector equation of a circle. All right, don't forget, arc length formula is from integrate from a lower limit to a certain upper limit. Then you find the magnitude of the differential radius, which is the vector equation that you'll be given. Find the magnitude of that differential radius. So first of all, differentiate the radius, which is the vector equation that you'll be given. Then find the magnitude of the differential radius. What you have, come and integrate. Whatever you integrate, then you substitute what? The limit into it. The result becomes your what? The circumference of the vector equation given. Right, so that is question number 2. Let's move on to question number. Okay, so this is question number 3. Okay, we want to evaluate this particular integrand, right? So from our lecture 1, we know that if you have an integration of this nature, integrate it term by term or component by component, right? So you pick I components, integrate. So you're going to pick this, then integrate, right? So pick this, integrate with respect to t, pick this, integrate with respect to t, pick this, integrate with respect to what? T, right? So you pick this, you know that this, you have to use what? The partial fraction first, right? Integration by partial fraction. Once you are done with that, then you come and substitute and what? Integrate, right? So this here, you know that this is basically the same as 1 over t minus 1 t plus 1, right? So use the partial fraction decomposition to decompose this. Once you are done, then you come and substitute and integrate, right? So this, when you integrate it well, right, you're going to have half ln into t plus 1 over t minus 1, right? When you integrate this very well, yeah, you're going to have half ln into t plus 1 over t minus 1. So that will be the result for the I component. And the j component, when you integrate the j component, 2j dt, you're going to have 2t g, right? And then the last component, which is the ln t, you know that when you integrate ln t, you're going to have t when you integrate ln t, you're going to have t ln t minus t. Okay, right? So don't forget, if you want to integrate ln t, you can't use mere integration. You have to use by parts. Okay, so if you are integrating ln t, right, then you let u equals what? Ln t, right? Then you let v, the v equals what? 1 dt, right? So if that is the case, then it means that we are going to integrate this, then we differentiate the ln t, because we know the result for integration, differentiation of ln t, and that is going to be what? 1 over what? T, right? So we come here, when you integrate 1 dt, you're going to have what? T, right? So this is the process we go through to integrate what? Ln t. And we know that the formula is what? uv minus what? Integral v du, right? So u is here as ln t, our v is what? As t. So we're going to have t ln t minus integral v du. So the v is t and du is what? Du is what? 1 over what? T. So this is basically du equals 1 on t dt, right? So this is what we have for du, so which is what? 1 on t. So this is t, 1 on t dt, right? So this cancels this, and we're going to have t ln t minus this, right? So when you move up here, it means that we're going to have t ln t minus integral dt, and this is basically t ln t minus what? T plus a constant c, right? So that is the process you go through to integrate what? Ln t. All right, don't forget, ln t cannot just be integrated merely like that. You have to just use by parts, right? So we let t, the ln function, be equal to what? The differential function. Then don't forget, this here is multiplied by what? 1, right? So once this is equal to what? The u, then this will be equal to what? The v, right? So you integrate this, then you differentiate it, because we know the result of the result when we integrate ln t, which is what? 1 on t, and we know the result that we will get when we integrate 1, right? And that is what? T. So we use that to get what? The integral of ln t dt, and that is basically t ln t minus what? T plus a constant c. So our final result for this is going to be half ln t half into t plus 1 minus t into t plus 1 over t minus 1. That is the I component. And the second component is going to be what? 2t plus 2tj. And the last component, which is the ln t, is going to be t plus t ln t minus what? T. Right. And that is the k component plus a constant c. So this is the solution for integrating what? This particular function. All right, so that is the end of problem number 3. Let's move on to problem number 4. Okay, so with question number 4, we want to find the parametric equation for the tangent line to the curve at this point, right? So this is the vector function that we have been given. So if you have a question of this nature, first of all, test the points that you have into, substitute each into the what? The function, and see if it will give you what? The points, right? The points that will give you the what? The vector function, or give you the all the points back, then that is the correct parametric value. So you do that substitution just to know your correct parametric value. So once you know the correct parametric value, then you go ahead and differentiate. So once you differentiate, you're going to substitute that correct parametric value into the differential function, right? Then you have your direction vector. So let's say that t is equal to what? Negative pi. So we're going to substitute t here, t as negative pi in here. Then we will know if this negative pi is going to give us, when you substitute into t cos t, is going to give us what? Pi, right? So you know that when you substitute cos into what? Cos into negative pi into cos, you're going to have what? Negative 1, right? You're going to have negative 1, and negative 1 times negative pi becomes what? Pi, right? So when you substitute negative pi into cos, you're going to have what? Negative 1. And don't forget, negative 1 times negative 1 times negative pi is going to have what? Pi, and that becomes what? The first component. When you substitute negative pi into this part, you're going to have what? Negative pi. When you substitute negative pi into the sign, you're going to have 0. You have 0, and that becomes, so that means that negative pi is the correct parametric value. So now, once you have the correct parametric value, you can go ahead and differentiate each of the components, right, to have the direction vector. So if you differentiate each of the components, then you substitute the correct parametric value, of which we have here to be what? Negative pi, into the differential radius to have what? The directional derivative, to have the directional vector, right? So once you have the directional vector, you know that always you multiply the direction vector with a constant, right? So you multiply that with a constant, then you add to the point to have your what? Equation, the parametric equation of the tangent line to the curve. So now let's find the derivative of the radius, right? So when we find the derivative of the radius, we are going to have derivative of cos. You know, we have to differentiate the t, so that we have what? Only the cos. Then we maintain the t, then we differentiate the cos. We're going to have minus t sine t, right? Or I. Then we come to the j portion. We differentiate the t. which is going to be what? 1. So we have plus j. Then plus, we differentiate t sine t, which is going to be sine t plus t cos t, right? So, okay. Okay, so now we have the differential radius. So we have to substitute the correct parameter, the parametric value into it to find the direction vector. So you substitute that, we're going to have, when we substitute negative pi into cos, we are going to have negative, we are going to have positive 1, right? So we're going to have positive 1. We know that when you substitute pi into sine, we're going to have 0. So this part goes off. So we have only 1i. Then we come to the j portion. We know that there is only j. So we're going to be what? Plus j. When we substitute negative pi into sine, you know that is 0. So we come here. We substitute negative pi into cos. We will have what? Positive 1, right? Positive 1 times pi. Positive 1 times negative pi becomes what? Negative pi or k, right? So this is what we have for the direction vector. So let me write it. Well, you're going to have 1, 1, and negative pi, right? So we have this, okay? You know that always we have to multiply the direction vector by a scalar, right? So we're going to have r prime of t to be equal to t times 1, 1, neg pi. Then we expand this, then add it to the initial point, right? So we're going to have our parametric equation to be equal to the initial point, which is pi, negative pi, 0, plus t of 1, 1, negative pi, right? So this, we expand this, we're going to have plus t, t, negative pi, t, right? So we add this to this, so we're going to have pi plus t. Then this to this, we're going to have negative pi plus t. Then this to this, we're going to have negative pi t, right? So this is our parametric equation. So we have to use the angle brackets. Okay, so this is the same as pi plus t or I minus pi plus t or j plus negative pi t or k. So it's either this or this. This is the angle bracket representation, and this is the position vector representation. All right, so this is the process you go through to find the parametric equation given the vector function, and then you are given a point, right? And want to find the parametric equation for the tangent line to a particular curve, right? So this is the process. Let's move on to question. Okay, so with question number 5, we want to find r of t, right? Said that r prime of t is equal to this vector, right? So if you want to find r of t given the differential of r of t, then it means that we have to integrate, right? And we have been given initial of r to be r of 1 equals what? J. So meaning that r of 1 is equal to what? 0i plus j plus 0 what? K. So we have to use these initials to find a constant for each component, right? So r prime of t is equal to square root of t I plus sine t minus 1 j plus 3t squared k, right? So we are going to go component wise, we integrate component wise, right? So we integrate the first part with respect to t, right? This is equal to t exponent half dt, right? So when you integrate this, you're going to have t exponent 3 on 2 over 3 on 2, so it will reciprocate, right? Plus a constant of integration. Okay, now this is what we have for the I component. So it means that we have to substitute r of what? 1 equals what? 0i. Okay, so that we can find a constant c1. All right, so it means that our t is equal to what? 1, right? So we put 1 in this to find the c and equate it to what? 0. So we're gonna have 2 over 3 into 1 over 3 on 2 plus c1 equals what? 0. You know, the I component here is 0, so we equate it to that to find the c1. So we're going to have 2 over 3 plus c1 equals what? 0. Okay, so we can see that our c1 is what? Negative 2 on what? 3. So this means that the first component is 2 over 3 t to the power 2 on 3 to the power 3 on 2 plus c1, and c1 is minus 2 on 3, so we have minus 2 on 3, right? So this is our I component. That is our I component. Okay, so this is basically the same as 2 on 3 out t on t to the 3 on 2 minus what? 1, and this is the I component, right? So this is the very basic way you can do this kind of work. Okay, so let's look at the second part, which is the j component. So we integrate that as well. So we're going to integrate the j component, which is integral sine into 1 minus t minus 1 dt, right? So we integrate this function. Okay, so you know that when integrate sine, you get negative cos. So you have negative cos into t minus what? 1, right? Plus a constant of integration, c1. And you know that when you integrate the inside, t minus 1, you're going to have what? 1. So it's the same function, right? Then we equate this to the initial. Initial here is what? 1j. So we're going to have what? 1 here. Okay, so that we can use that to find what? The constant c1. So what I'm trying to say is that r of 1 is equal to what? 1. So whatever we see t, you put what? 1. So we're going to have negative cos into 1 minus 1 plus c1 equals what? 1. Okay, and we know that this is going to be what? Cos 0 plus c1 equals what? 1. And cos 0 is basically 1, right? So we're going to have negative into 1 plus c1 equals what? 1. So this means that our c, okay, we are using c2, right? So this means that our c2 is equal to 1 plus 1, which is equal to what? 2. Okay, so that is the second component. So that is the second component. So we can see that now we have our C2 to be what? 2. So we substitute into what? This, right? So we have negative cos into t minus 1. Then our C2 is what? 2. So plus 2 or g, right? But we can rewrite this as 2 minus cos into t minus 1 or g, right? So this is the second component that we integrated, right? So the last component, which is what? 3t squared. I'm going to do the same work. I'm going to do the same work. So the last component, 3t squared, when we integrate this with respect to t, we're going to have 3t cubed over 3 plus a constant c3, right? So we have t cubed plus c3. Okay, so this, we are going to use the initial. So r of 1 is equal to what? 0k, right? So meaning that t is equal to 1. So we do that after we equate to 0. So we're going to have 1 cube plus c3 is equal to 0. So this means that our c3 is what? Negative 1. Okay, so we substitute c3 into the results here to have the third component. So that means that our third component is t cubed minus 1 or k. All right, so we have I, we have j, and we have k. So we can combine it and have what? R of t. So we combine that. So we're going to have R of t to be equal to the I, 2 on 3 into t to the 3 on 2 minus 1. Then the j component plus 2 minus cos into t minus 1 or j. Then the k component plus t cubed minus 1 or k. Okay, so this is our R of t that we obtained. All right, so whenever you have a question of this nature and you want to find R of t, given the differential of R of t, and as well you have the initials, don't forget that if you have R of 0 equals, let's say, I plus j plus k, then it means that your t, when you integrate, for instance, you're having t squared plus c1, that means that your t is what? 0. But if you have R of 1 equals the same thing, that means that your t is what? Now 1. Okay, so you do that substitution to find your c1. Don't forget that R of 0 is equal to what? 1 I plus j plus k. So if you substitute t equals what? 1 into what? The integrated function, then you equate it to what? The initial, right? To find the constant. All right, so that is the process you go through to solve this kind of question. Let's move on to question number 6. With question number 6, we have to determine the domain of the vector function given by R of t equals this function, right? So this means that we have to check for the condition that will make sure that each of these components, the value of t that we will substitute will make the function what? To be defined, right? So we have to check each component, right? So with the I component, which is this part, we know that we have 1 minus what? 2t or exponent half, right? And this is the same as square root of what? 1 minus 2t. And you know that any expression each side or under a square root sign should be greater or equal to 0, right? So we can say that 1 minus 2t should be greater or equal to 0. So this means that minus 2t is greater or equal to what? Negative 1. So you have t to be what? Less than or equal to what? Half. So this is for the first component, which is this, right? So we have to move on to the second component and check the value that is going to work for it. So the second component, which is e to the 2t sine pi t, right? We know that this, with this, every value, it will satisfy for every value, right? So with that one, we don't worry about that. So this is defined for all real numbers. So this is defined for all real numbers. So this will be defined for all real numbers. Whatever value you put here is going to make this thing defined, right? So for the second component, we don't have problem with that. So we have to come to the third component where we have ln into t plus 1 over t minus 1. Right, so this is where the case is, right? So don't forget, this is a function inside the logarithmic function, right? The natural log function. And don't forget, any expression or any argument that is inside the natural log function has to be positive, right? So t plus 1 over t minus 1 must be positive, right? So for this function to be defined, then if we are considering that both numerator and denominator are positive, then it will be what? Defined. If we are also saying that both numerator and denominator should be what? Negative, then the function should be what? Defined. So we say that both numerator and denominator must be positive or negative. All right. So if that is going to work, then we can say that. So let's write the first component somewhere. So we had t less than or equal to what? Half. Right. So we have that down. So let's come here for the third component, right? So we are saying that both numerator and denominator should be what? Positive, right? So it means that t plus 1 and t minus 1 should be what? Positive. So it means that t should be what? Greater than 0. So we're going to have t to be what? Greater than 1. Okay. And if they are all going to be negative, then it means that t plus 1 and t minus 1 should be less than what? 0. Right? So if you are considering all to be positive, all should be positive, both numerator and denominator. If you're also considering that both numerator and denominator should be negative, then all should be, right? So with that, then we can say that we have this to be what? Negative 1, right? So we can say that we have positive 1 and we have negative 1. So this means that our domain will have to exclude negative infinity and negative 1, and also exclude positive 1 to infinity, right? So since we have negative 1 and we have positive 1, that means that our domain has to be negative infinity to negative 1, or positive 1 to infinity. It should be exclusive, right? So this is our domain for the natural log function, right? So now we're going to combine the first component where we have t to be less than or equal to half, and the second component which comprises of all real numbers, and the second component which have negative infinity and negative 1 exclusive, and positive 1 and positive infinity exclusive. So we're going to combine this and that, right? So 1, 2, 3, 4. We combine them. So when we do that, it means that we're going to choose this to be their intersection, right? So we will say that the domain will be equal to negative infinity and negative 1. Okay, so the domain will be negative infinity to negative 1 exclusive for this particular function. All right, we had the first component to be what? Less than or equal to half. The second component comprises of all real numbers, and the third component was negative infinity to negative 1 exclusive, or positive infinity, positive 1 to positive infinity exclusive. So when you draw the number line, the intersection is going to be negative infinity to positive 1 exclusive. All right, and that will make this function to be what? Defined, and that it becomes the domain. So that is question number 6. Okay, so with question number 7, we want to find a smooth parameterization for the semicircle in the plane that passes through the points 2, 0, 0, 2, and negative 2, 0. For the semicircle in the plane that passes through 2, 0, 0, 2, and negative 2, 0, right? So we just want to find a smooth parameterization. All right, so you can see that these 3 points will lie on the circle, right? So these 3 points lies on the circle, right? So let me try okay, on the upper half of a circle. It lies on the upper half of a circle. So let's say that this is our plane and this is the point 2, 0. So it means that 2 will be somewhere here and 0. So it's going to be on the same line, right? And then 0, 2. So 0, 2, we're going to have something around this section, and then negative 2, 0. So we're going to have something around here, right? So it's a circle. So we say this is a semicircle, right? Right? This is a semicircle in the plane that passes through the point 2, 0, 0, 2, and negative 2. So these 3 points lies on the upper half of a circle, right? So when you join this, you're going to have a full circle. Okay, so the upper half, you know that this is what? 0, 2. This is 2, 0, 2, 0, 0, 2, and negative 2, 0, right? So these 3 points lies on the upper half of a circle. So this is, they are basically centered at the origin. So centered at the origin. Okay, so these 3 points, they are centered at the origin. You can see they are all centered at the origin. So now we can say that 2, 0 and -2, 0. Okay, they are basically opposite ends of, they are basically on the opposite end of the diameter. Opposite end of the diameter on the x-axis. On the x-axis. So this and this, they are the opposite ends of the diameter. So this is our diameter, okay, and this point and this point, they are on the opposite end of the diameter. Okay, we can see from there. Third, we know that 0, 2 lies directly above the origin, suggesting a semicircle centered at 0, 0 with radius 2. Okay, so you can see that 0, 2 lies directly above the origin. So we can see it here, lies directly above the origin, suggesting a semicircle centered at 0, 0 with radius 2. Okay, so once we know this information, then we can say that the circle is x squared plus y squared equals what? 2 squared. And that is basically x squared plus y squared equals what? 4. Okay, so this is the circle. So step 2. Now that we know the circle, we have to do what? We have to parameterize it, right? So step 2, we have to parameterize the upper semicircle. So step 2, parameterize the upper semicircle. Okay, we have to parameterize the upper semicircle. The general parametric form of a circle of radius r that centered at the center A and B is x of t equals what? x of t equals what? E plus r cos t, and y of t equals what? B plus r sine t, right? So we know this informations, then we can say that since our semicircle is centered at 0, 0 and has radius r equals 2, then we can say that the full circle, is s of t equals 2 cos t, and y of t equals what? They say 2 sine t, right? So we have 2 sine t. Okay, so that is for t that belongs to what? 0 and 2 pi inclusive. So that will be the range. Okay, so for t that belongs to what? 0 and 2 pi. Okay, but this one we want what? Semicircle, right? We want to find a smooth parameterization for the semicircle in the plane that passes through this. So if this is having a range of 0 and 2 pi, they mean that the semicircle will have what? 0 and what? Pi, right? 0 and pi. So but we only want the upper semicircle, right? So since we only want the upper semicircle, which starts at 2, 0 and rises to 0, 2, start at 2, 0 and rises to what? 0, 2, and also ends at -2, 0. Then our smooth parameterization will happen. Then that happens when we are going to have a range of 0 and pi, right? So if we are interested in the semicircle, then it's going to be what? 0 and pi. But if it is a full circle, then it's going to remain 0 and what? 2 pi as the range. So this, we're going to say that our r of t will be equal to 2 cos t I plus 2 sine t j on the range 0 less than or equal to t less than or equal to pi, right? So this is our smooth parameterization for this question. All right, so that is for question number 7. If you have a question of this nature, this is a practical question. So you try to sketch something so that it will guide you. All right, so that is the process we go through to have the solution for question number 7. Now let's move on to question number 8. We want to find the parametric equation of x minus 2 all squared minus y plus 2 plus 3 all squared over 4. And that is equal to what? -1. So basically, what this question is trying to ask is that we want to write this parametric equation. We want to write parametric representation, use what? Trigonometric functions, right? We want to write parametric representation using what? Trigonometric functions, right? So first of all, we have to basically we are interested in the trigonometric functions like tant and sectant, right? So we are going to represent this in the trigonometric representation, right? So first of all, we have to rewrite in the standard form of a hyperbola, right? So we have to change this into the standard form of a hyperbola, right? We know that this is a lookalike of a hyperbola representation, but we have to change it to the standard form so that we can use the identities of that. So we're going to say that x minus 2 all squared minus y plus 3 all squared over 4 is equal to what? -1, right? So we're going to divide here by -1, divide here by -1, divide here by -1, so that this part becomes positive, right? So we're going to have y plus 3 all squared over 4 minus x minus 2 all squared equals what? +1. Right. So once we have this, then you know that this is the standard form of a hyperbola, right? Of a vertical hyperbola. So now we use the trigonometric identity, right? So we know that the standard form of a vertical hyperbola is basically y squared over a squared minus x squared over what? B squared, and that is equal to what? +1. Right. So now that we have that representation, then we can go ahead and do the substitution with the trick, right? So in this case, we have this here equals 1, right? So we can say that you know that this is basically showing some characteristics of what? Sec and tan, right? Don't forget that sec squared is equal to what? Tan plus what? 1, right? So if you bring this here, you're going to have what? This is tan squared. So you're going to have sec squared t minus what? Tan squared t equals what? 1. So that is the same identity this thing is possessing, right? So that is basically the identity we are going to use. So we can see that feature in here. All right. So now we have to, now that we know that this is its trigonometric identity is this, then we have to parameterize it, right? So let me write it well so that we can parameterize this. Okay, so we're going to parameterize this using the identity, right? So we see that y plus 3 over 2, right, should be equal to what? Sec t. Okay, so this means that y plus 3, I just went away with the square, right? You know that this is y plus 3 all squared over 4, right? This is the same as y plus 3 all squared over what? 2 squared, right? And we are using the vertical hyperbola representation, right? So this means that since we are using just square sec, that means that we're going to use what? Only the information here, right? So we have this equals the sec, right? So we have y plus 3 equals 2 sec t, right? So making y the subject, we're going to have y equals what? Negative 3 plus 2 sec t, right? So we have y equals 2 sec t minus 3, and that is the j component, right? And also we say that x minus 2 should be equal to the tan, right? So we have x to be equal to 2 plus tan t, 2 plus tan t. So in a nutshell, we say that this is our I component, right? So our parametric equation will be giving us r of t equals the I component, which is 2 plus tan t, and the j component, which is 2 sec t minus 3, right? 2 sec t minus 3. Okay, so that is our parametric equation to this particular problem. All right, so that is question number 8. Now let's move on to question number 9. With question number 9, I've tackled the same question in lecture 1. So I'm not going to go through each of the process. I'm just going to guide you through so that it will just be a record. This is a question in lecture 1, right? So you know that if you have a question of this nature, a moving particle that starts at initial position r of 0 equals this initials with initial velocity, this acceleration is given, and you want to find a position at time t, what you need to do is to utilize your acceleration given, right? So you integrate the acceleration and you get what? Velocity. So don't forget, if you are integrating the acceleration, integrate it term by term, so that you have the I component plus a constant, the j component plus a constant, the k component plus a constant, so that you can fix in the initials for the velocity to find a constant for each component. Are you okay? So that you're going to have, let's say this part you integrate 4t, and you're going to have 4t squared over 2 plus a constant c1, right? So this is basically 2t squared plus what? C1. So using the initials, it means that v of 0 is equal to what? I. And this is the I component. So if t is equal to what? 0, then you're going to put 0 here. You're going to have what? 0 plus what? C1 equals what? 1. So it means that C1 is what? 1. Okay? So you have for the first component, you have what? 2t squared plus what? 1. Right? You do the same thing for the second component. Then when you are done obtaining the velocity, you integrate the velocity again to have what? The position at time t. Now, don't forget that one to integrate it what? Component wise. All right. So if you integrate component wise, then you substitute the initials to find what? The actual position at time t. So when you do it very well, you're going to have the position at time t to be equal to 2 over 3 t cubed plus 1, 2 over 3 t cubed plus t plus 1, or I plus t cubed minus t, or j plus half t squared plus t, or k. Okay, so if you do this and do it very well, this is the position you are going to have at time t. 2 on 3 t cubed plus t plus 1, or I plus t cubed minus t, or j plus half t squared plus t, or k. And that becomes the position at time t given this problem. All right, so that is the end of question number 9. Let's move on to question number 10. Okay, so with question number 10, we know that if you have the vector valued function, okay, and you want to find the direction vector of that particular direction vector valued function, all you need to do is to differentiate each component, and then those results you have becomes your what? The direction vector of that particular vector valued function, right? So this here, we're going to differentiate this, right? So when you differentiate 3t squared plus 4t all over 2t, this can be simplified to what? 3 on 2 t plus what? 2. When you differentiate that, you're going to have what? 3 on 2. So that is the first part. The second part, we have what? Minus into 2 plus t all on 2j, right? So when you simplify this, we're going to have this. We're going to have this, right? So when you differentiate this, we're going to have what? Half inside minus j. So meaning that we have the second part to be what? Minus half. The third part, we have what? 12 minus 2t over 3. When you simplify this, we're going to have 4 minus what? 2 on 3t. When you differentiate this, we're going to have what? Minus 2 on 3. Right? So basically, we're going to have what? Minus 2 on 3. And that becomes the direction vector given this vector valued function. So therefore, we can see that our direction vector is given as this. 3 on 2, comma, minus 1 on 2, comma, minus 2 on 3 as our direction vector. All right, let's move on to question number 11. We are to redefine this particular function, right? So that the function will be what? Continuous. Okay, for r of t to be continuous, right? For r of t to be continuous. So we have to consider them component wise, right? So this means that when we take limit as t approaches 2, they said t should not be equal to 2 if t is not equal to 2, and also if t is equal to what? 2. So we are considering if t is equal to what? 2. So this means that the first part is going to be what? R1 of t, limit as t approaches 2 of R1 of t, comma, limit as t approaches 2 of R2 of t, comma, limit as t approaches 2 of R3 of what? Of R3 of t, right? So this is what we are going to handle. This is what we are going to deal with. Okay, so we take it one after the other. So the first part, we know that limit as t approaches 2 of e to the what? 2t, 2 pi, we're going to have the same function, right? So this we're going to have e to the what? 2t. So the same function, because we don't have any t in it. So that is the same function we're going to have. And the second part, limit as t approaches to square root of 2t minus what? 2, all over what? 2 minus t. Okay, so this part is where a little bit work is. You know, when you substitute 2 into this, you're going to have what? Square root of 2 times 2, which is 4. 4, square root of 4 is 2. 2 minus 2 is what? 0. When you put 2, you're going to have 2 minus 2, which is what? 0. So meaning that we have what? 0 over 0, which shows that it is indeterminate. So once it is indeterminate, it means that we can differentiate numerator and denominator using the what? The L'Hopital's rule. So we differentiate square root of 2, which is the same as, or half, minus 2, right? So when we do that, we're going to have 2 times half t to the what? Negative half, right? So we're going to have 1 over square root of what? T, right? So now if t approaches what? If t approaches 2, what are we going to have? If t approaches 2, then, so this is the numerator, right? So let's try to differentiate the denominator as well. So with the denominator, with respect to t, right, of 2 minus t, right? So when you differentiate this with respect to t, you're going to have what? Minus 1. So now we can say that limit as t approaches 2 of 1 over square root of t all over negative 1, which is the same as limit as t approaches 2 of negative 1 of what? 1 over square root of what? T, right? So now as t approaches 2, we're going to have equals negative 1 over what? Square root of what? 2, right? So that is what we are going to have for that particular section. All right, there is 2 in there, so meaning that we are going to have 2t here, right? So it's going to be square root of 4. Okay, so it's going to be square root of 4. Okay, so we're going to have negative 1 over what? Square root of 4, and that is what? Negative 1 on what? 2. So meaning that the second component, when we apply the limit on it, limit as t approaches 2 of this particular function, we are having what? Negative half, right? So once we have the second component, then means we can move on to the last component, which is what? Laying into what? T cubed minus t squared. So we're going to have limit as t approaches 2 of t cubed minus t squared, right? So this will be equal to 2 cubed minus what? 2 squared, and that will be equal to limit into what? 4. So that is the last part, right? So this is how we are going to redefine the function. So the first part is going to remain the same. So the first part is going to remain the same. So we're going to have e to the 2t, comma. The second part we had minus half. And the last part we have what? Lane 4. Right? We have lane 4. Okay, so that is the solution to this particular problem. This is how you redefine this function to be continuous. this is how you redefine the function to be the continuous, right? So that is the end of question number 11. So now let's move on to question number 12 and look at how we can deal with if r of x, y, and z is equal to this function, right? So you know that total differential, you have to differentiate partially with respect to x times full differential of x plus partial with respect to y times full differential of y plus partial differential of z times full differential of what? Z. So we're going to apply the same information here. But don't forget, this is two functions multiplied. So if you want to differentiate, you have to apply what? The product rule. So we differentiate first with respect to x. So we're going to have what? E to the y, then times total differential of x plus second we differentiate with respect to y and it's going to remain the same. So we have what? X to the y dy, and this is I, right? And the second part we differentiate with respect to z. So we have 2z to z, right? This is the j part plus, you know that when you differentiate cosec x, you're going to have cosec cot x, right? So we're going to have minus cosec cot minus cosec cot s, right? And this is times total differential dx, right? So this is the k component, right? So you can say that our final solution is what? E to the y dx plus x e to the y dy I plus 2z dz minus csc cot x dx. Okay, so that is how you handle total differential problems. All right, so that is the end of question number 12. Let's move on to question number 13. Okay, so with question number 13, you want to find the derivative of f cross j, where f of t is equal to this and j of t is equal to what? Length t. Okay, so once you see cross, it means that you're going to use what? A cross product. So f cross j will be equal to I j k, right? So you position them correctly, minus 3 CSCT, and then we have 0, 0, ln t, right? So we're going to apply the limits, the determinant approach. So we're going to have minus 3, 0, CSCT ln t minus j 2 sec t 0. Then we have CST ln t plus k into 2 sec t 0, and then minus 3, 0, right? So we're going to have our result to be I into this and this. We have what? Minus 3 ln t. This and this is 0, so minus 0. Minus j into this and this will give us 2 sec t ln t, right? Minus 0 plus k into this and this is 0. This and this is also 0. So 0 minus 0. So finally we have the I components to be what? Minus 3 ln t or I. Then this and this becomes minus ln t minus 2 ln t sec t or j. So this and this is also 0. So we can see that this is the same as f cross g is equal to minus 3 ln t using the angle bracket minus 2 ln t sec t, right? So this is the same result as this as well. So that is the end of question number 13. Let's move on to question number 14. So with question number 14, we want to find um we want to find the directional derivative of this function, right, at the point -1 and 2 in the direction that makes an angle of pi on 3 with the positive x-axis. Okay, so this directional derivative kind of problem, we've solved a number of them and we know how to solve it. But this instance, we have been given in the direction that makes an angle of what? Pi on 3 with the positive x-axis. So this is a new frame of question, right? So you know that in finding the directional derivative is what? The gradient times the unit vector in the direction of the what? The vector, right? So you have something of this x naught, y naught, right? Which is, this is the point of the gradient, right? So now we have been given this, right? Which makes an angle of what? Pi on 3 with the positive x-axis. So this is what we are going to do. First, let's begin to find the gradient, right? So we know that the function we have been given is f of x and y, 3x squared minus 2y, right? So fs will be equal to 6x, right? So this implies that fs at the point -1 and 2 will be equal to -6. So basically it's -6i, right? So we have the first part. Then fy will be equal to -2, right? So meaning that if we try to substitute at the point -1 and 2, we are going to still have -2, right? So we have -2j. So that means that the gradient is what? -6i, -2j, right? So this is what we are going to use. All right, this is what we are going to use. So we can decide to use the angle bracket form, right? So this is what we have for the gradient. Now we need the direction vector in the unit vector, right? So this instance, we have been given in the direction that makes an angle of pi on 3 with a positive x-axis, right? So with that, note that if you want to find the unit vector, it is equal to cos theta sine theta, right? So you know that this theta here is it is the angle measured from what? The positive x-axis. So always the angle here, theta, is measured from the positive x-axis. So if you are given the problem where it is not measured from the positive x-axis, then you have to convert to that particular standard before you can use it, right? But in this instance, we have been given correctly from the positive x-axis, so we don't need to do any conversion, right? So in here, we're just going to substitute pi on 3 into that, so that we will have our unit vector, right? So we're going to do that substitution in there. So we're going to say that our theta is equal to what? Pi on 3, right? So we have our unit vector to be equal to what? Cos into pi on 3, comma, sine into pi on 3, right? So we can say that our unit vector will be equal to cos pi on 3 is half, right? Cos pi on 3 is half. So we have half here. Then sine pi on 3 is square root of 3 over 2. So we're going to have square root of 3 over 2. All right. So always, if you are given the unit vector, right, you are given in the direction that makes an angle of, it can be any angle, right, with the positive x-axis, then this is what you are going to use. It means that you're going to substitute the angle into this to find what your unit vector. So this is the unit vector we have obtained. So we just need to dot this with this to have a what directional derivative. But what if we were not given in the positive x-axis and we're given in the y-axis or the negative x-axis or negative y-axis? What do we do? How do we convert? We'll do all that. So let's finish with this problem. Then I'll give you the conversion table, right? So our gradient to this, our directional derivative, our directional derivative, our directional derivative will be equal to -6, -2 dot half, comma, square root of 3 over 2, right? So this is basically equal to this times this give us -6 over 2, right? This times this will give us -2 square root of 3 over 2, right? So this is basically going to give us -3. Then this will cancel this. We're going to have minus square root of 3, right? So we have -3 minus square root of 3, and that is our final solution, right? So our directional derivative, is giving us -3 minus square root of 3. And this can be represented as -3 out, 1 plus 1 over square root of 3. All right, so this is the same as this. So our directional derivative to this particular problem is -3 minus square root of 3, which is the same as -3 out, 1 plus 1 over square root of 3. Now, let me give you the conversion table where, if, for instance, it is not measured in the standard form, that is from the positive x-axis, and maybe you are given in the negative y-axis or negative x-axis or positive y-axis, how do you convert? So now okay, so this is the conversion table. Okay, so if you are given, this is the given direction given, right? So if you are given the direction that alpha is from positive x-axis, then the angle you're going to use theta equals what? Alpha, right? That means that your unit vector will be cos theta sine theta, right? So that will be your unit vector, right? Cos theta, comma, sine theta, right? But if you are measured, the measurement is from positive y-axis, then your angle is going to be pi on 2 minus what? Alpha. Alpha is the angle that you were given, right? So you have cos pi on 2 minus alpha, comma, sine into pi on 2 minus alpha, right? Then if you are measured, the measurement is from the negative x-axis, then this is what is going to be your unit vector will be cos into pi minus alpha, cos into pi minus alpha, comma, sine into pi minus alpha, right? And also, if it's from the negative y-axis, then it's going to be cos into 3 pi on 2 minus alpha, comma, sine into 3 pi on 2 minus what? Alpha. Okay, so that is how you do your conversion. Whenever you have your measurement that is not measured from the positive x-axis, then this is the conversion that you're going to do. If it is from the positive x-axis, then straightforward. You don't have any conversion to do, right? You're going to use the angle given directly. But if it is from the positive y-axis, then it means that you have to take the angle that you have been given from pi on 2. So now you're going to have pi on 2 minus alpha, which is the angle you have been given, right? Minus pi on 2. So you take that, cos into that, then sine into that. So this is the I component, this is the j component. And also, if it is from the negative x-axis, then it's going to be pi minus alpha. So we have cos into pi minus alpha, then sine into pi minus what? Alpha. And then from negative y-axis, then the angle theta from x-axis is going to be what? Pi, 3 pi on 2 minus what? Alpha. So your unit vector will be what? Cos into 3 pi on 2 minus what? Alpha, comma, sine into 3 pi on 2 minus alpha. So that is the conversion table. All right, so that is the end of question number 14. Now let's move on to question number 15. So with question number 15, we have been given this vector valued function, right? Of which we have here. And we want to find the fixed point on the line R of t, right? So in here, we have to do some small reading in here. So first of all, what is a fixed point, right? So a fixed point of a vector value function R of t is a point on the line such that R of t naught is equal to constant point, comma, and independent of t, right? But since all point of R of t changes as t changes, a fixed point would typically mean the point on the line R of t does not change position with respect to some geometric interpretation. So, 2, based on the standard interpretation, especially in vector calculus, when a question 6 find a fixed point, right, on a line, then it is typically interpreted as the point on a line that remains fixed when the parameter t is what is such that when the parameter t is such that the vector from the origin to the point equals the position vector, that is the point r of t naught, such that the vector does not what? Change its direction after some transformation or shift. So what it's trying to say is that no matter what you do, that fixed point, if you have a shift or transformation, that fixed point does not change. So maybe the fixed point could be something like 2, 3, 4, 1, right? But you can't have 3t, right? Because if there is a transformation and you have 3t, it means that you're going to change. It's going to be, if there is a change in t, like let's say t changes to 1, then means that this is going to be what, 3. But if t changes to 2, it means that this is going to be what, 6, right? So it means that it has to be constant, right? So you have to find a point on the line R of t that is fixed in space. So we have to do this calculation. So let's r of t naught equals r of t naught so r of t naught basically means that r of 0, right? So meaning that you are going to substitute 0 in place of what? T. So we're going to have r of 0 equals, when we substitute 0 here, we're going to have 0 here. So we're going to have negative 1 I. Then the j portion is going to be what? It's going to be 0 over 2 j minus, when you substitute 0 here, you're going to have 3, right? So we have 3 k, right? So we have negative I plus 0j minus 3k. So this becomes our fixed point. So our fixed point will be negative 1, 0, and negative 3, right? So the fixed point basically means where the particle is located when t is equal to 0, and it lies on the line traced by the vector function, right? So it lies on the line traced by the vector function. So this point, this fixed point that we have, any transformation that happens on this vector value function is not going to change, or is not going to shift this fixed point, right? That is why at the fixed point t is equal to 0. So note, at the fixed point t is equal to 0. So once t is equal to 0, then you're going to have constant. Okay, so that is question number 15. Let's move on to question number 16. We want to evaluate this limit. Okay, so we have to treat them term by term, right? So with the first term, we pick lim as t approaches infinity, 3e to the negative 2 lim t here, right? This we have here, we have to apply the properties, the log properties to do this, right? So this is equal to 3e to the t to the what? Negative 2, right? We raise this here to have what? Negative 2. So this we have here, we can say that we're going to have we're going to have 3 ln e times t to the negative 2, because we brought the exponent to the front, and then we're going to have ln e is equal to 1, right? So we're going to have 3 into 1 times t to the negative 2. So we're going to have 3t negative 2. So this is basically equal to 3 over what? T squared, right? So after using the logarithmic properties, this is what we have. So this here, when we try to substitute infinity in place of this t here, we're going to have what? When you substitute infinity in there, you're going to have 0, right? You know that 3 over infinity is 0. So we're going to have lim as t approaches infinity, 3e to the negative 2t equals what? 3 over what? Infinity. And this is equal to what? 0, right? So you know that anything over infinity is what? 0. Okay, so we have 0 here. Now we have to consider the second part, which is what? Lim as t approaches infinity, t squared plus t cubed over 2t cubed plus 1. Right, so with this, we have to do some kind of algebraic manipulations, right? So with that, we can say that we are factoring t to the 3 out. So when we do that, then we're going to have lim as t approaches infinity, t cubed out. Then we have 1 plus 1 over t inside. When you send this back, you're going to have t cubed. Then when you send this, you're going to have t squared, right? All over. So the denominator, to reapply the same principle, then I'm going to have t cubed out. Then we're going to have 2 plus 1 over t cubed, right? 1 over t cubed, right? So this is what we have. So we can see that this cancels this, and then we are going to have lim as t approaches infinity of 1 plus 1 over t all over 2 plus 1 over t cubed. Okay, so this is basically going to make the work so easy for us, right? So now we can substitute the infinity into the simplified expression. So in here, we're going to have, when you substitute infinity here, we're going to have 1 plus 1 over infinity all over 2 plus 1 over what? Infinity, right? And this is equal to 1 plus 0 over 2 plus what? 0, which is equal to what? 1 over 2. So the second component, we have what? 1 over 2. Okay, we have to deal with the last component, then we can combine all and look at the evaluated results. So with the last component, lim as t approaches infinity, e to the negative t, we know that when you substitute infinity here, we're going to have 0. E to the power, e to the infinity is going to give us what? 0. So in a nutshell, we're going to combine all. So we have 0i plus the second component, we have what? Half j. And the third component, we have what? Plus 0k. So in all, we have our result to be what? Half j. Okay, so the second component was what give us a significant value, which is half j. Okay, so this is how if you have a problem of this nature, just deal with it component by component, component by component. If you try to work all out at a goal, you'll be having challenge on the way. So we considered this, simplified it to, before we were able to substitute the infinity, and we got, once we simplified it and substituted the infinity, we had 0. And also this, when we simplified it and substituted the infinity, we had what? Half. And also the last component, when we substituted infinity, we had what? 0. So after doing all that and doing our combining all terms, we had what? Our result was half g, half g. And that is question number 16. Now let's move on to question number 17. So with question number 17, we want to evaluate this integrand, right? So you know that when you have an integrand of this nature, this is t e to the what? Negative 2t. This is a product function. And when you have two functions multiplying and you want to integrate, you have to use what? By part, right? So this is by part, but they've made the work so easy for us. So you know what we are going to do? We are going to use the tabular method, which is the DI method. I always like that when I'm dealing with smart work. Okay, so this is our, let's leave the component, right? So this is our work, t e to the what? Negative 2t. So if you want to use the tabular method, then our u will be equal to what? T. And our v will be equal to what? E to the what? Negative 2t. So our u is the function that we are going to differentiate to a constant. Always choose the u to be the function that you can differentiate to a constant. And the v is the function that whatever you do to it, it will never reduce. Okay, so we are going to differentiate that, integrate that part. Okay, so we have this. So we differentiate t and we have 1. We differentiate 1 and we have 0. Now we come here. we integrate e to the negative 2t, and we have negative e to the negative 2t over what? 2. We integrate again, and we have e to the negative 2t over what? 4. Okay, so this is what we have. Now that we have the result, don't forget that when you are dealing with by parts, it's uv minus integral v du. So meaning that this is positive, this is negative. If there is another third component, it's going to go positive in that order. So it means plus, minus, plus, minus, plus, minus, plus, minus in that order. So we are going to use the same idea in here. So we distribute the signs. So this to this, right? So that is positive. Then this to this, that is negative. Very simple. So this to that, this to that. Okay, so we're going to have this multiplying this. So we're going to have negative t e to the negative 2t all over what? 2, right? Then this to that is going to be what? Minus e to the negative 2t all over 4. Because of this minus, it's going to affect that. Okay, so this is our result using by parts. Okay, if you are to use the traditional method, which is the formula approach, you're going to do a lot of work. So this is a short way to do it when it comes to objective wise. Okay, now we have been given limits, right? From 0 to what? Infinity. From 0 to pi. So we're going to do that. 0 to pi. Okay, so we substitute pi into this where t is. So we're going to have negative pi e to the negative 2 pi over 2 minus e to the what? Negative 2 pi over 4. Then minus, when you substitute 0 in here, because of the t multiplying this, we're going to go what? 0. So we have to come here. So we're going to have minus into what? Minus e to the what? Negative 2 into what? 0 all over what? 4. Okay, so this is what we have. So this is basically going to be what? Minus pi e to the negative 2 pi over 2 minus e to the negative 2 pi over 4, right? And this is going to be what? Positive. So we have plus e to the negative 2 pi over what? 4. Okay, so let's try to combine the common terms. So when we combine the common terms, yeah, this is e to the power negative 2 into what? 0. So this is into what? 0, right? So that we have negative pi e to the negative 2 pi over what? 2 minus e to the negative 2 pi over 4 plus e to the 0 is what? 1. So we have 1 over what? 4. Okay, so you see how swift we have been able to go with the DI method. Now that we have that, we can say that, this result, we can still simplify it to have pi over 4 into 1 on pi minus 2 e to the negative 2 pi minus e to the negative 2 pi over 4, right? We can still express this in this way. And this all is multiplied by the I, j, and k. So we have I minus j minus what? K. And that becomes our solution. So simple, right? So, always when it comes to objective and you have two functions multiplying, you want to integrate, try to use the DI method, and it's going to make it work so swift. So this is the final result for evaluating this integrand. Okay, so let's move on to question number 8. So with question number 18, we want to find a vector equation that represents the curve of intersection of the parabolic cylinder z equals 2 minus x squared and the circular cylinder x squared plus y squared equals 2. Okay, so first of all, we have to know what we have been given, right? So in here, we have been given two surfaces of parabolic cylinder, right? So the first surface is what? Z is equal to 2 minus what? S squared. So that should be our equation 1. And the second surface is what? S squared plus y squared equals what? 2. So let's name that equation 2. So we have to find uh, a vector equation that describes the curve, where these two surfaces what intersect, right? So step 1, we have to understand the surfaces. We have to understand the surfaces very well before we can do this. And then we know that surface 1, we know that we have z equals what? 2 minus x squared. So this is basically a parabolic cylinder, right? That opens downward in the xz plane. It's a parabolic cylinder that opens downward in the xz plane. All right, so xz plane, right? So for each value of y, the curve in the xz plane is a parabola, right? So for each value of y, the curve in the xz plane is a parabola. Okay, so once we know this information about the surface 1, then we have to look at surface 2, where we have x squared plus y squared equals 2, right? So with that, we know that this is a cylinder, right? A circular cylinder. Okay, so this is a circular cylinder. So x squared plus y squared equals what? 2, right? That is a circular cylinder that describes a vertical tube that is infinite in the z direction. It is infinite in the z direction because you see we have x squared plus y squared equals what? 2. So it describes a vertical tube that is infinite in the z direction. So this is basically telling us that in the xy plane, it's a circle of what? Radius square root of 2. So radius r is equal to what? Square root of 2, right? We know that radius is what? R squared. So if it's r squared, then it's going to be what? Square root of 2 before we can get what? R in there. Okay, so this is the radius to this particular what? Circle. Okay, now step 3. Let's use the circular cylinder to define x and y. Okay, we have to use this circular cylinder to define x and y. So we have to parameterize the circle x squared plus y squared equals 2. Okay, so using the trigonometric functions, we know that x will be equal to what? 2 square root of 2 cos t, and y will be equal to what? Square root of 2 sine t. Okay, so we consider this to be what? Equation 3, and this to be equation 4, right? So we are using the trigonometric functions. So you know that the x column is going to be what? The radius times what? Cos theta, cos t, and then The y is going to be what? The radius times what? Sine t. Okay. Don't forget that t ranges from 0 to 2 pi exclusive. 0 to 2 pi exclusive. Okay? Because this is a circular cylinder, right? And it's a standard way of moving around the circle of radius square root of 2. As t increases, then we know what happens there. So let's look at step 4. Step 4, we will put equation 1 where we have z equals what? 2 minus what? S squared, right? So we put equation 1 into the parabolic surface to get z, right? So, okay, this is what we have here. We know this is 3. So we're going to put it here to have z, because we have z equals what? 2 minus x squared. And then we have x here to be what? Square root of 2 cos t. So when we do that, we're going to have z equals 2 minus square root of 2 cos t all squared, right? So we have 2 minus 2 cos squared t, right? So this becomes what? Our uh, z component. So we have z equals 2 out, 1 minus what? Cos squared t. And don't forget that 1 minus cos squared t represent sine squared t, right? So we say that our z is equal to 2 sine squared t. That is beautiful, right? So, you know, the trigonometric identity cos squared c plus sine squared c equals 1. So if you have 1 minus cos squared t, then it means that sine squared t was make the subject. So you have sine squared t is equal to 1 minus cos squared t. So we substitute sine squared t in place of this. Then we have 2 sine squared t. So now we have our x component, we have a y component, and we have our z component. So we can just write our vector equation, right? So we're going to write our vector equation. So our vector equation, r of t, will be equal to square root of 2 cos ti plus square root of 2 sine t j plus 2 sine squared t k. Right, so this is basically the same as using the angle bracket square root of 2 cos t, comma, square root of 2 sine t, comma, 2 sine squared t close angle brackets. So this becomes our final solution to this particular problem. All right. So that is the process we go through to find a vector equation that represents the curve of intersection of the parabolic cylinder and the circular cylinder x squared plus y squared equals 2. Go through the process, go over, and you'll get the whole idea. Okay, now let's move on to question number 19. Number 19, we want to find the area of the parametric equation given this, right? So with this kind of problem, first of all, you have to understand that cos and sine are periodic function with period 2 pi, right? So they traces the entire ellipse once, right? So the area of the parametric equation for this vector function, this parametric equation where u is greater than 0 and v is also greater than 0, we have to follow these steps, right? So first of all, we have to understand the curve type involved in this parametric equation, right? So let's say that u should be equal to what? X should be equal to what? U cos t, and y should be equal to what? V sine t, right? So if that is the case, we have to understand the shape, right? Before we can do that, we have to eliminate t, right? So we have to make t the subject. So in here, we're going to say that x on u is equal to what? Cos t. So we have cos t is equal to what? X on u. And then we have to make here too the same thing. We have sine t is equal to what? Y on v. Okay, so recall that from trigonometric functions, we know that cos squared t plus sine squared t is equal to what? Positive 1, right? So we have to use that identity to evaluate this problem. So we're going to say that, this is basically cos t is equal to x over what? U. And we have sine t is equal to y over what? U. So we can do some kind of algebraic manipulations, right? So when we try to square both sides, we're going to have what? Cos squared t equals what? X squared over what? U squared. And sine squared t is equal to what? Y squared over what? V squared, right? So since this and this is equal to 1, then we can say that when you add this and this, we're going to have what? 1. So we're going to have x squared over u squared plus y squared over v squared is equal to what? 1. And this can be expressed as x over u all squared plus y over v all squared equals what? 1. Okay, so this is what we have. So the curve is an ellipse. You can see that this is basically portraying the identity of an ellipse, right? So centered at the origin with semi-major axis u and semi-minor axis v. So we have to use the area formula for parametric curves. So the area enclosed by the parametric curve. The area enclosed by the parametric curve r of t is equal to s of t, comma, y of t. So over one full cycle, right? So this is basically going to be, our area is going to be from a limit of what? T1 to T2 half x of t times y prime of t minus y of t times x prime of t, or the t, right? So we know our x, we know our y. So what do? We have to find the derivative of x and the derivative of y so that we can use this formula, right? So we're going to have our x prime of t to be equal to, when you differentiate u cos t, you're going to have what? Negative u sine t. So we're going to have negative u sine t. And when you differentiate y equals v sine t, you're going to have what? V cos t. So we have v cos t. Okay, so we have all that we need. So we're just going to substitute in here to find our area. So when we do that substitution, we're going to have our area to be equal to what? uv cos squared t plus uv sine squared t. And this is basically equal to, you know, this is common to this. So we're going to have uv into cos squared t plus sine squared t, right? And this is what? uv into what? 1, right? So after substituting x prime of t, y prime of t, combining, or we have this, right? So we have our area, we have uv, right? So now we are going to take the integral. So we're going to find the integration of that. We're going to find integration of that. So we're going to have our area to be equal to, from 0 to 2 pi, from 0 to 2 pi, half uv dt, right? So we are dealing, we are using this for a full cycle, right? You know that full cycle is what? From 0 to what? 2 pi. So we have half uv out, then integral of what? T is going to be what? T. Integral of 1 dt is going to be what? T, from 0 to what? 2 pi. So when we do that substitution, we're going to have 2 pi minus 0. So basically we're going to have 2 uv pi over what? 2. And that is equal to what? uv pi. So our area is equal to what? Pi uv. Pi uv. Okay, so this is our area of the parametric equation given u cos t, v sine t. This is the process you go through to get your area of a parametric equation given this. You can watch over to get the whole concept again. Okay, now let's move on to question number 20, which is our last part of the question. So with question number 20, you want to find a unit vector that is perpendicular to the curve at 2, 1, and -1. Assuming that the curve x squared y minus 2xz plus 2y squared z to the 4 equals what? 10. Now, when you have a question of this form, first of all, find the gradient. Okay, find the gradient. After that, you try to normalize the vector, right? So you find the gradient, then after that, you normalize the vector and make it a unit vector, right? So we are going to find the gradient of this. So when you differentiate with respect to x, we're going to have 2x minus 2z. Okay, we are differentiating this with respect to x, and we have 2x minus what? 2z. At the point 2, 1, -1 will be equal to what? 2 into 2 minus 2 into what? -1. And that is equal to 4 plus 2, which is equal to what? 6. So our first value at the point 2, 1, -1 is what? 6. So we have 6i. And then we differentiate with respect to y. When you differentiate this function with respect to y, we're going to have x squared plus 4y z to the 4, right? So at the point 2, 1, -1, we're going to have 2 squared plus 4 into 1 into -1 to the 4, right? So we're going to have 4 plus 4 into 1, and that is equal to 8. So meaning that we have 8j. So that is the second component. Now the third component, we're going to have fz, the differentiating with respect to z. So we're going to have minus 2x plus 8 y squared z to the 3, right? So fz at the point 2, 1, negative 1 will be equal to negative 2 into 2 plus 8 into 1 squared into negative 1 cube. So that will be equal to minus 4 plus 8 into minus 1. So that is minus 4 minus 8 is equal to what? Minus 12. Right? So this means that fz is equal to what? Minus 12p. Okay, so this is our gradient. Okay, this is our gradient. So we have to normalize this vector to make it a unit vector. So we have our gradient to be equal to the first is what? 6, the second is what? 8, and the last is minus 12. Okay, so we're going to normalize it to make it a unit vector. So in doing that, meaning we have to find the magnitude of this. So the magnitude of that will be equal to square root of 6 squared plus 8 squared plus 12 negative 12 squared, and that is equal to square root of 244. Square root of 244. So once we have that, you know that can be simplified to square root of 244 can be simplified to 2 times square root of what? 61. Okay, so this is our magnitude. We are normalizing it. So we have the magnitude, we have the unit position vector. So we just divide this by this to have what? Our normalized vector. So, and that becomes our unit vector perpendicular to the curve. So that will be equal to 6, 8, negative 12 all over 2 square root of 61, right? So this is the same as when we factor 2 out here, we're going to have 2 out, 3, 4, negative 6, right? All over 2 square root of 61. So this cancels this, and we're going to have 3, 4, 6 all over square root of 61, right? So this becomes our result for finding the vector that is perpendicular to the curve. That is 3, 4, next 6 all over square root of 61, or 1 over square root of 61 times 3, 4, 6, negative 6. Okay, and this becomes our final answer to this particular problem. So you can go over and go over again till you get a concept in all. That is the end of the problem, and that is the end of the lecture. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and please, I really appreciate your comments. Do comments, okay? And then share with your mate as well. On to the next video. Please keep learning and stay inspired. Bye bye.